Hello, my name is Soborno Berry. I'm from Berry Science Lab. Schrodinger wave equation. Let me tell you a story. The Schrodinger wave equation, invented by Austrian physicist Erwin Schrodinger, he won the Nobel Prize in 1933. The Schrodinger wave equation set the foundation of quantum physics immediately. Bad news is that quantum physics is kind of hard, and Schrodinger's wave equation is even harder. So now let me ask you a question. What is the most famous equation in the entire universe? You guessed it! It is Newton's second law. F is ma. So, why do we love F equals ma so much? You ask, can we eat it? No way! So why do we love it so much? It can explain the future of object. Yeah, the momentum and the position of just one object. Unfortunately, Newton's law doesn't work in quantum mechanics because quantum mechanics is only the law of small things, such as protons, electrons, and neutrons. And that's the end of my story. Now, I'll show you the math. Also, I forgot to mention that there are two kinds of Schrodinger wave equations. Number one is time-independent Schrodinger wave equation. Number two is time-dependent Schrodinger wave equation. Right now, we're doing the time-independent Schrodinger equation. So, energy is kinetic energy plus potential energy. Kinetic energy's equation, as you know, is equal to half mv squared. And then PE is replaced with U. Or momentum is mv, right? But let's take a bit of a walk here. Let's whole square both sides. P squared is m squared v squared. Now divide both sides by 2m. M goes to m squared m times. So p squared over 2m is half mv squared. So E is p squared over 2m plus u. Now basically we're using all the substitutes we could find. Okay, so now that part 1 is done, let's do part 2. This is going to be the longest part. I is e raised to the I kx minus omega t. Let's take the derivative side. d psi over dx is equal to ik times e raised to the I kx minus omega t. But e raised to the I kx minus omega t is equal to psi, right? So we can use that instead. Now let's take the second derivative, which leads us to even more math. D squared psi over dx squared. So d squared psi over dx squared is equal to ik whole squared times psi. Now, ik whole squared actually means we square both of them, as shown in the last problem. I mean in the last part, where we whole squared p and mv, and then after we whole squared mv, we got m squared v squared. So d squared psi over dx squared is equal to I squared k squared times psi. But wait, I is actually an imaginary number, actually defined until it was found by scientists. So the value of it was -1. I is the square root of -1. that means I squared must be equal to the square root of -1 whole squared. But square root and square root cancel, which means that -1 remains. So I squared is -1. So d squared over d squared psi over the x squared, okay, is equal to -k squared times psi. But wait, we need to do something in order to continue our second derivative. Now, in order to continue our argument, we must stop for a minute. Now, we have to find k. So k is 2 pi over lambda. Now, we cannot just run off with just this explanation. We have to go through a long process. Not very long though. First, let's do cross multiplication. Lambda k is 2 pi. Also, if you haven't heard of pi before, it's an irrational number. We round it to 3.14, or to be infinitely precise, we just use the symbol pi. Pi is like this. It's like a line, but with two little tails curling under it. So now we bring k to the other side since we want to find lambda. So lambda is 2 pi over k. Now let's use de Broglie's hypothesis. Or de Broglie means the broccoli. You get it, bro. You get it. It's funny jokes, right? So, lambda is h over p. That's the hypothesis. Now let's do cross multiplication. Lambda p is h, but we want to find p. So p is h over lambda. So that is h times 1 over lambda, or h times lambda raised to the -1. I'm saving space, okay? Okay. So let's stop there. Now, what is lambda? That is equal to 2 pi over k. Since there's a -1 here, we have to flip it. So h times k over 2 pi, which is just hk over 2 pi. But if you ask me, h over 2 pi is reduced Planck constant, which looks like h, but there's a bar on its pole. So that's reduced Planck constant k. They call it h bar abbreviation. Psi over dx squared is equal to negative p. Wait a second, but p is equal to reduced Planck constant times k, right? But we tried to find k, so that is p over reduced Planck constant. So that's negative p squared over reduced Planck constant squared times psi. Now let's put reduced Planck constant squared on both sides. Reduced Planck constant squared d squared psi over dx squared times negative p squared over h equal to negative p squared over h squared times psi, and put a reduced Planck constant squared there. Cancel. D squared psi over dx squared times reduced Planck constant squared is equal to minus p squared psi. And that is the end of part 2. Over 2m plus psi plus u. If you haven't seen, it is right here. That circle on It's right there. Right there. Now, let's multiply everything by side. You know what hit your buddy? Psi hit you. The square side of 2m plus psi u. So, psi, wait, p squared psi. But it states here that d squared psi over dx squared times reduced tan constant squared is a negative p squared psi. So positive p squared psi must mean the negative goes to the other side. So let's write that. Psi e is psi over dx squared times reduced tan constant squared over 2m plus psi u. And that is the time-independent Schrodinger equation. That was a lot of work. Now let's do the time-dependent. E is reduced tan constant omega. Psi is e raised to the I kx minus omega t. Okay, so let's take the derivative of psi. D psi over dt, since it's in control of the next part now. I omega since times psi. E is reduced tan constant times omega. Okay? Now let's multiply both sides by psi. Psi e is psi reduced tan constant omega. Now let's divide everything by 8. Psi e over 8 is psi reduced tan constant omega over 8. Oh, I forgot. They were reduced too. So 8 cancels. So reduced psi e over reduced tan constant is psi w over psi double. Okay, now let's multiply both sides by I. Okay, so let's see. Now we have, okay. So let's multiply both sides by negative I now. Negative I over reduced tan constant times e, psi e, is equal to negative I psi omega. I forgot to put a psi here, so I'll do that now. So let's replace it now. Negative I over reduced tan constant psi e is negative d psi over dt. Since this thing is all negative. Oh wait, it's negative, so it's positive. So let's see. After it's negative I times reduced tan constant times negative I over reduced tan constant times psi e is equal to d psi over dt times negative I8. Okay. Phew! We don't need to back up a bit. We're perfectly fine. So, okay, so 8 cancel. Negative I squared times psi e is d psi over dt times negative I8. But wait a second here. Negative I squared. That's the I has a value of the square root of negative 1. So that's the negative of negative 1 squared. Squared cancel, and negative plus. So that's just 1 or nothing, and basically in multiplication. So psi e is equal to d psi over dt times negative I8. So let's use that instead of psi e. D psi over dt times negative I8 is equal to, write that down. Psi over dx squared times reduced tan constant squared over 2m plus psi. And that is the time-dependent Schrodinger equation. We did part 1 like an hour ago, And we reviewed that. So now let's review part 2. We found a new letter, psi, but we learned that it also had an exponent. It had a value of e raised to the I kx minus omega t. We took the derivative of psi, and we found out that it was ik times psi itself. The value of psi, well, then we took the second derivative of psi, and we found out a lot after that. We did de Broglie's, or should I say, the Broglie's hypothesis, which is lambda equals h over p. We found out that k was 2 pi over lambda, but to be precise, it was actually p over reduced Planck constant. And we also found out that reduced Planck constant was 2 pi over k. We discovered a lot in part 2. But part 3 was even more chaotic. We got the end of part 1 and placed it here. We put the law of part 1 and plugged it to there. We multiplied everything by psi, and then we stated that negative p squared psi was d squared psi or dx squared times reduced Planck constant squared. And since it's positive, the other sign must be negative. So, and that led us to the time-independent Schrodinger equation. We did a lot in the time-dependent, but that's just boring. So thank you for watching. I hope this video inspired you to fall in love with math and science, and hopefully subscribe to our channel, Berry Science Lab. Is the Schrodinger equation. I know this looks ugly, but don't run away. I'm going to talk about what the Schrodinger equation actually means, and hopefully you'll see it doesn't deserve its bad reputation. Physics tries to predict the future. What I mean is, if you have an object in some state that you know, and then you do something to it, well, you let it go above the ground, or you give it a big push, or you put it next to something electric. The job of physics is to tell you what happens to the object. Newtonian mechanics did a good job of that. If you know the initial position and velocity of an object, it will tell you exactly where the particle is at any time in the future. What we want for quantum mechanics is something that will do the same. Tell us what the future state of the system is. That's what the Schrodinger equation is for. And quantum wave functions are described by the Schrodinger wave equation. Though the behavior of all subatomic particles are inherently probabilistic, Schrodinger's equation does not itself contain any probability. The probability of every possible observation is determined by the wave function, but prior to the observation, the wave function changes and evolves in a completely deterministic manner. This deterministic is in which a wave function behaves without any observer present is what Schrodinger's equation describes. Charged particles exert forces on one another. We can view this by saying that at different points in space, a charged particle has a different amount of energy. The height of this graph at each point in space is represented by the variable v. The height does not represent the spatial dimension at the value of the potential energy for our charged particle at each location. And we represents the mass of the particle. Reduced Planck constant is Planck's constant over 2 times pi. Psi, which looks like a fork, represents the value of the wave function at each point in space at time. This graph shows a wave function along just one of the 3 spatial dimensions. At each point in space and time, the wave function is a complex number with a real A component and an imaginary component. This expression indicates how much the wave function changes as x increases by a small amount. This change is a complex number which can be represented with the arrows as shown. Austrian physicist Erwin Schrodinger is one of the founders of quantum mechanics, but he's most famous for something he never actually did, a dot experiment involving a cat. He imagined taking a cat and placing it in a sealed box with a device that had a 50% chance of killing the cat in the next hour. At the end of that hour, he asked, "What is the state of the cat?" Common sense suggests that the cat is alive or dead, but Schrodinger pointed out that according to quantum physics, at the instant before the box is opened, the cat is equal parts alive and dead at the same time. It's only when the box is opened that we see a single definite state. Until then, the cat is a blur of probability, half one thing and half the other. This seems absurd, which was Schrodinger's point. Seeing though, Schrodinger's cat is very real. In fact, it's essential. If it weren't possible for quantum objects to be in 2 states at once, the computer you're using to watch this video couldn't exist. The quantum phenomenon of superposition is a consequence of the dual particle and wave nature of everything. In order for an object to have a wavelength, it must extend over some region of space, which means it occupies many positions at the same time. The wavelength of an object limited to a small region of space can't be perfectly defined, though, so it exists in many different wavelengths at the same time. We don't see these wave properties for everyday objects because the wavelength increases as the momentum increases. And the cat is relatively big and heavy. If we took a single atom and blew it up to the size of the solar system, the wavelength of a cat running from a physicist would be as small as an atom within that solar system. That's far too small to detect, so we'll never see wave behavior from a cat. A tiny particle like an electron, though, can show dramatic evidence of its dual nature. If we shoot electrons one at a time in a set of 2 narrow slits in a barrier, each electron on the far side is detecting electrons one at a time at a set of 2 narrow slits cut in a barrier. Each electron on the far side is detected at a single place at a specific instant, like a particle. But if you repeat this experiment many times, keeping track of all the individual detections, you'll see them trace out a pattern that's characteristic of wave behavior. A set of stripes, regions with many electrons, separated by regions where there are none at all. Block one of the slits and the stripes go away. This shows that the pattern is a result of each going through both slits at the same time. A single electron isn't choosing to go left and right, but left and right simultaneously. This superposition of states also leads to modern technology. An electron near the nucleus of an atom exists in a spread-out, wave-like orbit. Bring two atoms close together, and the electrons don't need to choose just one atom, but are shared between them. This is how some chemical bonds form. IE equals to negative d squared psi over d x squared times the Dutch constant squared over 2m plus psi u equals to negative d squared psi over dx squared times a reduced squared constant squared over 2m plus psi